This is lecture 4 on the theme of decidability, and it's a computer theory type course called Introduction to Theory of Computation. It's a mixed senior level M1, that's first year master's level course. The single author is Sipser, Michael Sipser. Here's the textbook that I'm using for this course. I have the Chinese version, as you can see, but if you take the English version, it'll probably look like this. It's a rather famous text, pretty well the Bible. You know, debatable, but it's a standard text, very popular around the world, used on theory of computation. So it was the one I chose. If a particular text tends to have the reputation of being the Bible, you know, like the main, most popular, most respected text in a particular field or topic, then I'll tend to choose it for that reason. I mean, if it's so popular and highly respected, therefore it must be good. Okay, so always like good text. More general things. If you want to know more about the text, how to get it, in two ways: either in paper form, you know, a hard copy form, in which case you have to pay for it. So you'd need to go, for example, to Amazon.com and get it perhaps second-hand. Or if you prefer it electronically, you can get it for free by downloading it from emule.com, E-M-U-L-E, emule.com, and just download it and put it onto your e-reader or whatever. Some people prefer hard copy, others prefer it electronically. If the price, even second-hand, the price of the book is too much for you, you can always get it for free, but then you have to have an e-reader of some sort, or a laptop or a desktop that you can read the textbook on. Okay. Now, for such details, you can go to my website. So, Prof, just short for Professor, Hugo, that's my given name, deGaris, that's my family name, at wordpress.com. And there are various tabs on this website, so click on the tab deGarisMPC. MPC, or deGaris family name. MPC is for mathematics, pure mathematics. P is for physics, so mathematical physics. And C is for computer theory. So these three branches. Although about 90% of the lectures, or the courses, will be on math and physics, because that's my primary thrust. Maybe 10% or so, or less, I guess, of courses will be on computer theory. Largely the pure mathematics of computation, because the main thrust basically is math. So it's math as applied to mathematical physics, and just pure math for its own sake. And critically, almost exclusively, except for these initial courses, about 24, more or less, at graduate level. So four levels, 4 course years of graduate level courses. M1, M2, in other words, first year masters, second year masters, and then PhD 1 and 2. First year PhD level courses and second year PhD level courses. So it gets quite advanced. Because I'm a free prof, a free professor, I'm free to do whatever I like, say whatever I like. So one of my intentions is actually to raise the bar, meaning to raise the standard of the topics discussed in these lectures, these courses that I'll give. Because I'm free, I can go as high as I like, and in practice, every university has some kind of cut-off point, right? You can get to such a high level that there are hardly any students taking that course, and so university administration, presidents and so on will not pay very high salaries for extremely qualified professors to teach a class of one student. Right? That's just not economic. So, but because I'm giving YouTube lectures, my public is potentially the whole planet, right? So, and because it's free, the lectures are free for you, the students, and free in the sense I'm free to do what I like, say what I like. I just stand in front of a camcorder and sprout words. I can, free. All right. Okay, so we're in chapter 4, and much anticipated chapter 4, where we talk about, well, the big highlight of the course is the very famous halting problem of Turing, which it won't be on this board. In fact, I think this chapter is in fact the shortest of the whole text, the whole course. So we're now into part 2 of the text on computability theory, and there are 4 chapters in this part, 3 parts in the whole text. And the second of those 4 is decidability, and it's only about 18 pages, so it's the shortest. I've marked at each chapter the number of pages it has. So just in a board or 2 after this one, we'll get to the famous halting problem. Now, why is it so famous, and why is it such a highlight? And it's one of the pillars, as I keep saying, of computer theory, because it's so counterintuitive in many ways. Most people, and the proverbial man on the street, probably has the idea that computers are all-powerful. Computers can do anything. Computers are approaching human-level intelligence and may go beyond human-level intelligence. Computers can think a million times faster than we can. They're sort of godlike in many ways. That's the growing impression of the capability, the power of computers. But once we finish this chapter, that myth, because it is a myth. All the things I've said are pretty well are true. I mean, computers will become incredibly powerful and fast and ultra intelligent and all that stuff. They're the next dominant species. Well, that's what I think, and a lot of people think. Once we finish chapter 4, it's my wife just coming out. I find her presence incredibly distracting. All my brain, left brain, thinking analytically, mathematically, just goes to mush, because then my right brain switches on furiously, I suspect. And I get all these distracting messages across the corpus callosum. That's the huge band of fibers that connect the 2 hemispheres, and utterly distracts my concentration on analytical things in the left brain. So that's my theory, anyway. Okay, so back to where I was. So chapter 4, with the halting problem, we will show that there are problems that a computer with an algorithm cannot, with any algorithm, in fact, we'll prove that, any algorithm cannot solve. Right? And that's a sobering realization, that there are problems that are simply mathematically provably unsolvable, right? And that's a jaw-dropping conclusion, and one of the great results to come out of theory of computation. Now, Turing, he wasn't actually the first to show this.